Hey guys, welcome back to Pop 'em Up Chem. In this video, we're going to be looking at nucleophilic substitution. So we're getting into the juicy stuff now. And I do want to mention that there is a difference between what HL and SL require from this. So just listen out for when I give that cue. We're going to be looking at defining what nucleophiles are, describing their reaction with halogenoalkanes, and then we're going to be comparing and contrasting the two different mechanisms by which this can occur. But firstly, I want you to draw and name the products if we distill ethanol with potassium permanganate. Let's go through it then. So we know if we draw out ethanol that we have a primary alcohol. We are distilling with our oxidizing agent. So if we're distilling, we're only going to go to our aldehyde. We're not going to get full oxidation to our carboxylic acid. So we're just going to remove the hydrogen from the oxygen and one of the hydrogens from the carbon to give us the aldehyde, which is ethanol. So what is a nucleophile? Well, we've already looked at electrophiles in this unit. A lot of files, a lot of loving going on in this unit. And we said that electrophiles loved electrons. It's in the name. So they loved negative charge centers. So where could we think nucleophiles would be attracted to? Well, the clue's in the name, the nucleus, and a nucleus has a positive charge. So indeed, nucleophiles love protons, or better said, they love positive charge centers. So the exact inverse of an electrophile. And these contain either a partial or a full negative charge, just the opposite of an electrophile. So halogenoalkanes are of huge importance to this process. Remember, we made these using the free radical substitution reaction that we could do to alkanes. The reason these are really important is they undergo this substitution reaction, which allows us to change the functional group on particular molecules, which can be very powerful. So that's just a summary of free radical substitution. But what's going on with nucleophilic substitution? Well, due to the carbon-halogen bond, which is very polar, what happens is we end up with a partial positive charge on the carbon, partial negative charge on the bromine. And this partial positive charge, caused by the shift of electrons towards bromine because it's more electronegative, makes it a site of attack for any potential nucleophiles. So one of the most common ways we do this is with a strong base. And it's quite simple. All that's going to happen is whatever halogen is attached to the alkane chain is going to be substituted by the alcohol group, and we're going to end up with the salt of whichever metal hydroxide we used. So in this case, it would be NaCl. You can see the switch. The conditions for this are aqueous hydroxide ions, of course, and we need to gently warm it. The reaction will still occur at room temperature, but usually we want to speed up the reaction as that would be slightly slow. But you're itching for those mechanisms, aren't you? I can feel it. So I just want to point out, differentiating between Sn1 and Sn2 reactions is a HL only. So you will not be examined on it, SL students. However, I do think understanding this fundamentally helps your understanding of organic chemistry and the reactions that we're studying. So what does Sn1 or Sn2 stand for? Well, simply substitution, nucleophilic 1 or 2. So why 1 and why 2? Where do those come from? Well, really, it's quite simple. The 1 comes from the number of reactants that are present in the rate determining step. So in an Sn1 reaction, we have 1 reactant in the rate determining step. In Sn2, we have 2 reactants in the rate determining step. This means both of the reactions will have slightly different rate equations. So if we have a look at the rate equation for the Sn1 reaction, we're only going to find 1 substance in the rate equation, hence 1. So we get something like rate equals K times the concentration of the halogenoalkane. Now, if we look at the rate equation for the Sn2, we're going to have the rate equals K halogenoalkane still the same. However, we're also going to be dependent on the concentration of whichever nucleophile we're using in the reaction. For the example we used on the previous slide, that would be OH- ions. So the rate determining step is, in the Sn1 reaction, the heterolytic break of the carbon halogen bond. We'll go over that in more detail. And the rate determining step for the Sn2 reaction is the attack of the electron deficient carbon from the incoming nucleophile. Again, the example I gave previously, that would have been the OH- ions. So we're still yet to look at the mechanism, but I still think it's important that we have this kind of general understanding of the reaction. So let's do a couple of questions on it. First question, why is Sn1 called unimolar? Pause the video. Pop them up. Yeah, indeed, the clue was in the name for this one reactant in the rate determining step. Next question, what are the conditions for nucleophilic substitution? Pause the video. Pop them up! So although we said we could do it at room temperature, the conditions for the reaction would be warm slightly with aqueous base, for example, NaOH. Let's take a closer look at the Sn1 reaction. So remember, this is the one with one molecule in the rate determining step. So let's take an example halogenoalkane. So I'm going to draw it in 3D projection for now so we can see the carbon. We're focused on this central carbon. So I've got two methyl groups, one bromine group, which is going to be delta negative, carbon's going to be delta positive, and I'll put the last group as a CH3 group as well. So what happens here is we get that heterolytic break of this bond. So this is going to be slow. This is the rate determining step. But look, there's only one molecule. The molecule is breaking itself apart. That is the initial step. That's going to leave us with this carbocation intermediate. And the OH that is in the solution will then act as the nucleophile and attack this carbocation, which will be very quick because it's negative and positive attracting, and we will then form the corresponding alcohol as the bromine will have been substituted, and then we will form the salt of whatever metal hydroxide we used as a base to give the nucleophile. So just to go back through that, because our rate determining step only contains one molecule, our rate equation is going to be rate times the concentration of the halogenoalkane. The concentration of the nucleophile is not involved. So how can this happen? Well, thinking back to what we covered in electrophilic addition, all of these side groups that are attached to this carbon give a positive inductive effect to stabilize that carbocation intermediate. Just like we needed when we were doing electrophilic addition, we need a stabilizer if we're going to form this carbocation intermediate. And so tertiary compounds will favor this mechanism. And this is the key to the Sn1 reaction. If we don't have that positive inductive effect, we're not going to be able to form the carbocation intermediate, and we're not going to undergo this reaction. Okay, so make sure you got some good notes on this, and remember, use your understanding of the positive inductive effect to think about what is going on in the reaction, as it's going to come in handy when we consider Sn2 also. Let me give you a question on that. What is the rate determining step in Sn1 nucleophilic substitution? Pause the video to have a go at that. So in Sn1 reactions, we only have one molecule in the rate determining step. So it's going to be that heterolytic break of the CX, where X is the halogen. It's going to be the heterolytic break of that bond and the halogen removing the electrons that is our rate determining step. So what's Sn2 anyway, and how is it different? As you asked. So here we have two molecules in the rate determining step. So I'm going to draw a 3D projection of a halogenoalkane here. And instead of the bromine being able to remove itself in that heterolytic split, the nucleophile is going to attack the partially positive carbon, which is going to lead to this intermediate anion, which is kind of a transition state. So it looks like it has 5 bonds, but really we're just talking about the bromines leaving, the OHs incoming. So the electrons are moving away with bromine. Now, this leads us to, again, the corresponding alcohol that's replaced the bromine. Now, the 3D projection and how that's different will matter when we come to look at stereoisomerism later in the unit, but don't worry about that just yet. So, what have we got? We've got 2 molecules, which means our rate equation is going to be rate equals the concentration of our halogenoalkane times the concentration of our nucleophile, which in this case is the hydroxide ion. Now, again, we can use the positive inductive effect to understand this. This is primary, so we only have limited amounts of positive inductive effect for a potential carbocation intermediate. So the bromine can't take those electrons with it, as there's only one methyl group in this case to stabilize that carbocation intermediate, and so therefore Sn1 reactions can't occur, and instead we have to form this transition state. Now, for HL students, it's important to remember that the angle of attack of this nucleophile is 180 degrees from the halogen, and we call this backside attack. I know I didn't name it, but that's a legitimate name. Okay, this can seem like a lot. How do you know which one of these is going to happen? Well, throughout the unit, as we've seen, primary, secondary, and tertiary are a huge influence on organic behavior, reaction behavior. So at one end of the spectrum, we've got tertiary compounds which will undergo Sn1, and at the other end, primary undergoing Sn2, with secondary somewhere in the middle. We're going to discuss some other factors later in HL, but that's not important at the moment. So if we have a primary halogenoalkane, we know that because the heterolytic bond break is unlikely, we're unlikely to form a primary carbocation because of the lack of positive inductive effect. So we're going to get an Sn2 reaction because that transition state can stabilize the reaction. At the other end of the spectrum, we have tertiary compounds, which, because of the groups that are attached to that carbon, the stabilizing effect of the positive inductive effect means that we can have that heterolytic break, and we're likely to form the tertiary carbocation because of the stabilizing effect of the rest of the molecule. So that means that we're going to form that carbocation intermediate, and we'll get the subsequent attack of the nucleophile. Let's just switch those around so they're the same as up top. Now, a secondary, we'll see that we do have some stabilizing effects of the positive inductive effect, but it's going to vary in probability depending on the molecule, on a few other things. But it's a good time to highlight that in organic chemistry, we're never going to get 100% of any reaction. We're going to have what we call major and minor products. That's what you're going to describe. The major products and the minor products will be the unlikely reactions. And that's how we should conceptualize thinking about which reaction will take place. It's more which reaction will occur more or less rather than 100% or not at all. Time to give yourself a little test then. What is the rate equation for an Sn2 reaction? Pause the video to give yourself a moment. Pop them up. So hopefully you got rate equals K times the concentration of the halogenoalkane multiplied by the concentration of the nucleophile. Next question. Write the organic product for the reaction between 2-bromobutane with aqueous sodium hydroxide. Pause the video. Pop them up. So if we draw out bromobutane, then we know we're going to remove the bromine group and we're going to replace it with an OH group because we've got the hydroxide ion. So it's not asking whether it's Sn1 or Sn2 at all. all we need to do is draw the same molecule with OH in place of the Br. The other product will be NaBr if we've had NaOH. So it could do either of the mechanisms because it's secondary, but that's not what the question asked. This one, draw and name the mechanism for the reaction of CCH3Cl and aqueous potassium hydroxide. Pause the video. Pop them up! So for this one, if we draw out the molecule, we see quite quickly that we have a tertiary halogenoalkane. If we have tertiary, then we know we're going to have an opportunity for a stable carbocation intermediate. So we're going to get a heterolytic bond break. The chlorine is going to leave with its electrons, giving us the carbocation intermediate that is stabilized by the groups around it and is then attacked by the nucleophile. This then forms our tertiary alcohol, and of course the salt of the metal from the hydroxide, which in this case is KCl. So this is of course an Sn1 reaction, which we know can occur because of the positive inductive effect of the side groups that are attached to the carbocation. So this can take quite a bit of getting used to. So the best thing to do here is, here's a question with a couple of parts. Take your time, have a go at them, and I'll go through all the answers in quite a bit of detail. Just really try and have a go at these, and instead of going forward in the video, if you need to, go back and have a look to support you. Pause the video and take your time. Okay, let's go through those. So I've bolded the ones here that I'm going to do mechanisms for as the question required, but I'm going to draw the overall reaction first. So I've got my bromoethane plus NaOH is going to, of course, go to ethanol plus NaBr. Now, this is a primary halogenoalkane. So with primary, we know we're going to get an Sn2 reaction because we can't stabilize it with the positive inductive effect. So we're going to have the nucleophile, which is the OH-, attacking the electron deficient carbon, remember with the backside attack opposite to the bromine, which is then going to form our transition state intermediate. And when I draw these, I like to start with the long range bond and then the 3 bonds that are going to remain from the groups that are already there, and then put the other long range bond out of the other side. And remember, it's an anion overall, so square brackets and the negative charge around it. So with our slow step done, our rate determining step, we then have our fast step, which is effectively the leaving of the leaving group bromine, leaving us with the primary alcohol product. We need to remember to also include our NaBr, which is our salt, and we would call this, of course, ethanol. Now with the second one, we're only going to write the equation for it because it could take either reaction, but there are 2 sites on this one which would be replaced with the OH group. So very simple, all we do is basically take the same molecule and just replace it with the OH in the brackets where the halogens were, and here we're going to form 2 different salts because we have 2 different leaving groups, the Cl and the I. With the last molecule, we've got a tertiary halogenoalkane, and we're just going to include the CH3 and the Cl on that 3rd carbon in our equation using our condensed structural formula. And basically, we're just going to use the exact same for our product, but we're just going to, where we have the Cl in the reactants, we're just going to replace that with the OH. And of course, as always, we're going to produce our salt, which in this case is NaCl. So when I'm drawing this mechanism, I'm going to these larger side chains. I'm just going to condense these and use them as written in that formula to make it easier to see what's going on with the carbon that's actually involved with the reaction. So we have a C2H5 side chain, a CH3, CH7, and a CH3. So in this situation, we know we've got enough groups to provide positive inductive effect. So we're going to have an Sn1 reaction on the polar bond between the carbon and the halogen. We're going to have a heterolytic bond break. The chlorine's going to take the 2 electrons with it, and that is going to give us a carbocation intermediate, and that carbocation intermediate will subsequently be attacked by the nucleophile, in this case the hydroxide ion, because it's around long enough, because it's stabilized by those side groups. That's going to give us the product of the tertiary alcohol. And don't forget your salt. So guys, don't worry if it's a bit overwhelming at first. With practice and really considering your positive inductive effect and the things that we've talked about throughout this unit together, this will all come in time. Thanks again for joining me. Make sure you like, subscribe, share the videos, and as always, practice makes slightly better.